Welcome students. This brief video will give us more examples of dissociation equations, ionization equations, and show us very easy how to determine what we call the Van Hoff factor. Okay, just want to make sure that we're clear on this. So if you are given a solute, so you are placing these, and we are definitely with the understanding that they are soluble in water. They will lead to a homogeneous mixture. So we may be asking, well, what about metallic? Well, it's very rare that a metallic substance will be soluble in water, so we don't even address it. Ionic soluble solutes dissociate. They break up into individual cations and anions because of the interaction with water, not a chemical reaction. They are already composed of the ions that then get separated. They dissociate. Because there's free moving ions, an ionic solute will be in solution in electrolyte. Covalent. Covalent substances do not break into ions. They're not made of ions. And unless they're acids, they don't ionize. So they are not made of free-flowing ions. So they don't get, if we had another column for non-electrolyte, they'd get checked. They can be soluble, but we're understanding that all of these are. Acids. Acids react with water, as shown in the previous video. We call that ionization. Because we are making free-moving ions, they are electrolytes. So let's go through some example equations. So let's take magnesium nitrate. It is ionic. It, in the presence of water, will dissociate. For every one of these, I get one magnesium, that is a +2 cation. Remember the labeling of charges, a +2 cation. For every one of these, I get 2 nitrate ions. So here we have more than one polyatomic ion, so that is indicated with that in parentheses and a 2 on the outside. So that becomes the ratio. I need 2 nitrates to balance the +2 of my magnesium to yield a neutral compound. This would be the dissociation equation. What about, let's take calcium nitride. Okay. Ionic, so we know it will dissociate. For every one of these, I get 3 calciums. We know calcium, being an alkaline earth metal, will be a +2 cation. And 2 nitrides, nitrogen, -3. And I need those aqueous labels because they're dissolved and then free-moving electrolyte. We'll do just one more. How about, let's do silver. Let's do silver acetate. Okay. Now, silver, remember, it's one of those transition metals that we always trust the charge of. It will be +1. That is acetate. There's only one of them. It's not in parentheses with the number outside. We will keep that together. All right. So let's talk about this Van Hoff factor. The Van Hoff factor, we just honored the gentleman that laid the experimental groundwork for it. All it conveys to us are the number of solute particles that is created when one solute formula is put into solution. All right. So sometimes the Van Hoff factor is given this like cursive I as a symbol. So what would the I value be for magnesium nitrate? Well, every one of these, I get 1 magnesium, but 2 nitrates. So the Van Hoff factor is 3. For every 1 calcium nitride, I get 3 plus 2, it would be 5 for, I guess I should put a 3, so I'm making a column, huh? Means for there. And for silver acetate, 1 and 1. So ionic compounds, we know, at least will be made of 1 cation and 1 anion. So the Van Hoff factor for soluble ionic minimally will be 2. Okay, well, what about something like glucose? So C6H, shoot. Mr. Antonelli, Mrs. Lamb would be so upset. I'm going to do glucose, or I'm sorry, sucrose. Oh, I could come up with glucose. But anyway, all right. Now we know covalent, it does not dissociate or ionize. You just get individual dissolved molecules. For every 1 of these, we get 1 of these. So the Van Hoff factor is 1. What about nitrogen? What if we dissolve nitrogen in water? Well, covalent. For every 1 of these, I get 1 solute. All right, but what about acids? Acids. They react with water. They react with water to create. And remember, acids give away the hydrogen ion. That's what makes an acid an acid. Water will take it. We will create hydronium. And then whatever is left over after it's lost the hydrogen is our other product. We're normally not doing Van Hoff factors for acids, but if we were, well, for every 1 of these, I get 2. Yeah? And we're looking at the number of ions, the number of solute particles that we'll have for every 1, because it's these that then lower the vapor pressure, increase boiling point, decrease freezing point, and it's all about the number of them. Let's just do another acid. How about perchloric? Okay, this, being an acid, donates the hydrogen ion. We are just going to be interacting our acids with water as far as this chapter is concerned. And so you don't have to worry about, doing this against any other reactant. We're looking at what do they do with water, just like what do these guys do in water. So, gives away the hydrogen ion, this takes it, I form H3O+, and then ClO4-. For every 1 of these, I get 2, Van Hoff factor being 2. So, hopefully that gives us more connection and practice with writing these equations. And then how do we get this Van Hoff factor? Sometimes it's represented as this little cursive I. And again, it's the number of solute particles that every 1 solute can possibly give us. So every 1 formula unit of silver acetate gives us 2, hence Van Hoff factor being 2. And also a nice reminder about these concepts. Okay, hopefully looking back, we did some examples of both and looked at that. Best of luck, ladies and gentlemen.